Hello and welcome. I'm Gabriele Ara, a Ph.D. student at Scuola Superiore Sant'Anna, Pisa. Today, I will present on behalf also of my supervisor, Professor Tommaso Cucinotta, and my fellow Ph.D. Agostino Mascitti, our most recent work, titled Simulating Execution Time and Power Consumption of Real-Time Tasks on Embedded Platforms. This work has been developed as part of the Ampere European project, a model-driven development framework for a highly parallel and energy-efficient computation supporting multi-criteria optimization. First, let's discuss the context of this work. When dealing with systems with real-time constraints, predictability is often one of the most important goals to achieve. However, it is also very difficult because it directly clashes with some unpredictable components in the hardware architecture of modern embedded platforms that are necessary to ensure a certain level of performance or to provide a certain degree of energy efficiency. Perhaps the most well-known technique in this regard is dynamic voltage and frequency scaling, or DVFS, which introduces for each CPU a specific set of operating performance points, or OPPs. Each OPP is characterized by a pair of voltage applied to the CPU and frequency selected for its switching activity. By dynamically changing from one OPP to another at runtime, DVFS can be used both to save power and energy and reduce the thermal output of a system when the highest performance is not a requirement. In the context of energy saving, heterogeneous multi-core architecture are another critical component of modern embedded platforms. In those architectures, different processor types can be dedicated to different tasks, reaching particularly energy-efficient operating points depending on current workload. Indeed, the success of ARM big.lit architecture proves the effectiveness of this approach when dealing with energy efficiency in embedded platforms. For real-time systems, predicting how various workloads will behave depending on the operating system condition can be very hard. A common practice of soft real-time system development is to disable the hardware capabilities that lead to non-predictable execution of real-time tasks. However, energy efficiency requirements cannot be ignored anymore in the design of modern, heterogeneous, and real-time computing platforms. Research on real-time systems often relies on non-functional simulators, which can simulate the timing and scheduling of real-time tasks depending on the scheduling strategy and system conditions. However, these simulators rarely implement energy-aware features, or they implement very simple theoretical models, thus rarely accurately reflecting the real platform behavior. For these reasons, there is a need for an open real-time simulation framework with support for power management features based on actual real embedded platforms. We thus introduced the Power-Aware Real-Time Profiler and Simulator. These are two new open-source tools for real-time researchers that wish to explore the depths of power-aware features on embedded platforms. The first is a tool that automates the profiling of a heterogeneous embedded platform under various DVFS conditions. Real application workloads are profiled on a target embedded platform, and key data and statistics are then extracted from those profiles in post-processing. These data extracted in post-processing and then in turn fed to the simulator. The simulator is an extension of the well-known RTC, which introduces a new automation for the definition of heterogeneous platforms with DVFS support by using a combination of user-supplied and automatically generated platform description files. The simulator can simulate both the power and timing behavior of actual real-time workloads based on the data collected by the profiler. We can divide our approach into two main phases: data collection and elaboration, and system simulation, each characterized by a few steps. In the first phase, the profiling suite is deployed on a target platform, on which it performs a set of automated profiling runs. The component that gets deployed on the target platform and performs the actual profiling is called the embedded component. In contrast, the host component typically runs on a workstation and manages data post-processing. Both software run on Linux platforms. The embedded component can be configured to execute a set of actual real-time workloads on a target platform under various DVFS settings. Profiling is typically performed over each possible DVFS configuration for each core island on heterogeneous platforms, with the possibility to start one up to n instances of the same task. The possibility of running multiple instances of each workload is crucial, as we will see later during this presentation. In simpler terms, the profiler sweeps all possible combinations of the selected CPU island, CPU frequency, workload type, and the number of instances of each task to execute on the same island. For each of those combinations, it profiles task execution under those conditions, collecting several metrics over time, namely execution time, power consumption, system temperature, and so forth. Once all data has been collected, the host component analyzes it offline and automatically extracts a set of statistics used to drive the simulation of the power and timing of those workloads within the simulator. The generated data, along with the system description provided by the user, is then fed to the simulator, which produces accurate traces of task execution under various real-time scheduling policies, along with the estimated power consumption. To do so, the simulator keeps track of task activation and termination and the per-CPU power consumption, calculating the final overall energy consumption over the course of the entire simulation. The power and timing simulated can also be used to drive real-time aware dynamic techniques for power saving, like selecting the appropriate OPP for real-time applications, or dynamically switching from one OPP to another to custom task placement strategies. Let me show you an example of how the simulator can be configured. To declare static properties of the hardware platform, the number of CPU islands, CPUs, and OPPs available for each island, the user can edit a simple YML file. The configuration file is also used to specify which models to use to simulate the power and timing behavior. For more complex platforms, characterized for example by multiple islands and different core types, like for example the ARM big.lit architectures or similars, multiple island specifications can be supplied, each associated with its own power and timing model. The simulator software will automatically instantiate all the required components to emulate a platform from the given description. Model specification is supplied in a separate CSV file generated by the post-processing component of the profiler tool. Given these tables, the simulator can pick the correct power consumption and speed estimation for each task, for each combination of CPU type, workload type, and frequency. In this regard, our simulator improves the original implementation of RTSim in that it does not make any assumption on how the execution time and power consumption will scale with respect to the CPU frequency. Combining these three values precisely identifies the correct table entry to estimate the variations in execution time and power consumption for the selected configuration. Basically, it just replaced the collected data by the profiler on the real target platform. For a multi-core CPU island, the simulator uses the following model to calculate the power consumption of an island with n CPU cores. Here, the PW is the power consumption measured by the profiler for an entire island when running that workload on a single core, while the P-idle is the power consumption when the entire island is idle. This reflects the fact that, as we will see, most embedded platforms lack per-core power monitors and provide power information only at the island level, or they do not have any embedded power monitor at all, and thus an external one must be used. For any input configuration, the speed at which task is running determines its simulated execution time. Similarly, the power consumption of the whole island is calculated using this given formula, in which the power consumption of the entire island when idle is summed up with the contribution of the active task on each core. Needless to say, proper selection of these parameters greatly influences the simulation accuracy, especially for multi-core platforms, as we will see later. To test our approach, we use three very different embedded platforms. We have the Odroid XU3, an heterogeneous multi-core platform with ARM big.lit architecture, Xilinx UltraScale Plus, and the Raspberry Pi 4. Of these platforms, The first two provide internal power monitors on a per-island basis, while the Raspberry Pi 4 provides no power monitor at all. For that platform, an external power monitor connected to its power supply has been used to collect the power consumption information during runtime. As already mentioned, the profiler application suits every possible combination of working conditions for each application workload for each platform. For this reason, we'll discuss here only a small representative subset of the collected data, inviting you to check out our publication for a more comprehensive evaluation. Here, we can see how several different workloads behave when varying the operating point on the same CPU type when run in isolation. That is, only one core per island is active at any time. In these experiments, workload types vary from hashing to compression to encryption and decryption algorithms. The plot on top represents the speed at which the tasks are executed, while the bottom one shows the registered power consumption, including the power consumption of the whole island when idle. When isolated, those workloads exhibit overall similar timing and power behaviors with respect to the selected CPU frequency. However, the situation changes when we try to increase the number of concurrent tasks executing in parallel on the same island. Under those circumstances, some tasks deviate from the expected behavior, most likely due to the effects of memory and cache interference. Regarding the execution speed of each task, the expected behavior would be that the tasks running on different cores but under the same conditions, like core type and CPU frequency, would take the same amount of time to complete. However, some of these tasks in our experiment start to slow down, most likely due to the increase in time spent in waiting for data to manipulate from main memory when run multiple instances in parallel. Similar effects are also visible for power consumption. The expected behavior in this case is that the average power consumption of the entire island increases linearly with the number of active cores running the same workload type. However, the more we increase the number of parallel tasks, the more time spent waiting for data from the main memory, thus reducing the average power consumption of individual CPUs. These effects can be accentuated by purposely written synthetic applications that stress the lowest level cache of the CPU to force specific rates of main memory accesses over time. The more we increase the cache miss ratio from 0 to 100%, the more these effects become more clearly visible. Given these results, it is clear that high-level, non-functional simulators may have a difficulty reproducing these effects for multiple platforms with exact precision. However, since the impact of these effects is limited for non-synthetic workloads, we can achieve an acceptable accuracy by adequately selecting the appropriate parameters when post-processing the data collected by the profiling tool. In our paper, we identified some different strategies for selecting each of these parameters that I'm briefly going to illustrate here, together with a quantitative evaluation of their effectiveness. First, let's talk about the execution time or speed of each task. Given the three variables that uniquely identify the working condition for a CPU, we can either select the speed measured by the task running in isolation, thus completely ignoring the effects that are showed from multiple platforms, and always use them to simulate the execution time, regardless of how many tasks are running in the system. Take the average speed for an increasing number of parallel tasks, or take the maximum registered execution time value, typically the one registered while multiple instances are running at the same time in parallel. The latter solution may be the safest for real-time task simulation, since it can be compared to what is usually referred as worst-case execution time. On the data collected during our extensive testing on the mentioned three platforms, the first two strategies provide a very similar degree of accuracy when comparing simulation results with collected data, achieving errors less than 10% up to the 19th percentile. Though they're not perfect, so some edge cases may result in some more significant simulation errors. Using the maximum value instead proved to be overall less accurate than the other approaches, but it has the added benefit that simulated execution times will never exceed the maximum registered value for each working condition, which can be a desired effect when simulating real-time systems. For the power consumption of the island when idle, we can take the measured value since we have it readily available. To select instead the PW, so when a task or workload is running on at least one of the cores, we can identify 3 more strategies. We can, again, ignore all interference effects and take the measured value for a single task in isolation as the power consumption value, or we can try to perform a linear regression. That can be done over an increasing number of parallel tasks, from 0, so when the whole island is idle, to up to n per island depending on the number of CPU cores. We can also calculate it as the slope that minimizes the overall error from no tasks to n tasks per island, after fixing the constant term of the regression to the idle power for no tasks running on the system. Among these approaches, the last one proved to be the most effective overall, achieving about 10% error up to the 19th percentile. Since we had to implement all of these approaches to evaluate their effectiveness, users of our tools can select which combination of these techniques to use when constructing the input tables for the simulator in the post-processing. Our paper discusses all of these results further, as well as implementation details, so please do check it out for a more complete evaluation. In addition, in the publication we also discuss lengthily how thermal effects can influence simulation results and the importance of adequately simulating the thermal output of an embedded platform to prevent unwanted issues due to thermal throttling effects. Results in this scope are still a work in progress detailed in our paper, but for the sake of brevity, these results will not be included in this presentation. And that brings us to the conclusion of my presentation. Feel free to check out the tools that I presented today. They are open source and available on GitHub, and feel free to contact me if you have any questions or follow-ups about this work. Thank you.